Hi everyone, my name's Dave. In this video we are going to show you how to take your planet data that we prepared in a previous video and build a machine learning model. Now here in this example that we used previously, we had an image with the different colors and the classification or the labels, and we use those two pieces of information to extract our data and prepare the data for building a model. Now, just to go over some of the data steps that we did before, let's go into Python, and what I'm going to do is I'm going to load up one of those files, and this is the data file that will contain the features of the image that we extracted. Actually, let's start off with the labels. If we just look at the unique values in that array of labels of our data, you'll see that we have three values, just three unique values, 1, 2, and 3, for the thousands of samples that are in there. Now, because in our machine learning algorithm, we want those values to be 0, 1, and 2, so we can simply subtract 1 from the labels. And we'll go over this again when we go through the code that actually builds the model. Now for the feature data, which I'm just calling data here, I load that. And that takes a while to load because there are many features, and they are, as you might remember, little pieces of imagery that are 64 by 64 pixels each. So now if we look at the shape there, so we have 278,050 samples, 4 bands, and then each image chip is 64 by 64 pixels. Now, what we need to do in the when we build the model is we need to transpose or kind of reorganize the data. Now, what this is doing here, actually I need to use the NumPy function for that. Now, as you can see here, we've reorganized the data so we have the number of samples, and then the 64 by 64 dimensions, and then at the end are the 4 bands of data. So that's, and we'll again go over that in the code. Now here, this is the code that will simply build the model. So the first part, we are loading up various packages. I recommend TensorFlow and Keras, and you can see that those are loaded here. Now these lines highlighted here load the features and the labels, as we just did in our interactive Python session before. Now what I'm doing here is it's just good practice to create or calculate some statistics for each of the bands. They can be useful for down the line, so I like to have those, and here we actually print that to the standard output. We print the means and standard deviations and mins and maxes. Now here I'm actually pulling out the features for the different classes or class labels that we have. And as you can see here in this comment, that's where I subtract the 1 from the labels. Now if you've already done that, you can comment that out, but in this case, I'm pulling out the labels that are class 0 or have labels 0, 1, and 2 for the clear, shadow, and cloud features. And then I do the same thing for the labels. So now I've separated these data based on their labels. And then I print out how many are in each of those labeled classes, because what we want to do is we want to balance the number of classes, so we have the same number of classes for each same number of samples for each class. Now the shadow class is the smallest. So what these lines here are doing are I'm removing, or I'm sampling the clouds and the clear features and labels for the number of shadow samples that exist, because that was the smallest class. So here I'm just replacing my cloud features and clear features and labels so that they all equal the number of samples that were in the shadow class, and so that all of them are equal. Now here I go and concatenate all of the features together into a new feature array and do the same thing for the labels. And it's important, of course, that these be in the same order. Here I'm doing clear, shadow, and cloud. And now I need to scale the data. And here I scale them, I'm just dividing them by a rough maximum value based on some of the statistics and a distribution of the data. So as you can see here, I load those then into a new array called feature scaled, and I do that for each of the 4 bands, which are each scaled differently. And then here I have my test proportion is I'm taking 60% of the data and using 40% as a test array. And then this function here is for splitting my data into those test and split arrays. So taking the proportions, I return a training set of X, or the features, a training set of Y, or the labels, and then similarly test for X and Y. Now the last thing I have to do is this transposition, transpose the data as I showed earlier in the interactive Python session. And see here, in order to get those 4 bands of data as the last dimension, I have to reorder those or transpose the data by taking the axes of 0, 2, 3, and 1. The 1 axis being the one with the 4 bands. And then when I print out the shape, I will see that my 4 bands of data of the different bands of imagery is in the last dimension. Now, in the next steps, after I print out the shapes there, the size of the arrays just as a confirmation, and then we're going to get into actually saving. Here I save those data just as to save them, knowing that this is exactly what went into my model. And then we start to actually build the model. And I'm not going to go into too many details here, but Keras is a very good framework to use for building these models. And I create a sequential model. That is, there are going to be sequences of layers that the input data are going to be processed into. And you can see in that convolution 2D layer, that first one, it has an input shape, which is the kernel size, or 64 by 64 by the number of bands. So that's the input, that's the shape of the input data. And the next layer is a dropout layer, and what that does, dropouts can help prevent overfitting of the data. So in this case, there's a 25% or 0.25 probability that I will ignore or forget the training of the previous layer. So there's a probability that's built into that to kind of prevent overfitting. And then I do another convolution, 2D convolution, but at a slightly different number of pixels of 48. And similarly, I can give these layers names so that they're easy to recognize in the summary. And then again, you can see I do another dropout after that. After that, I take all those data from those layers and I flatten it out so that I have all of them, all of those extra convolutions and other parameters that it's generated, and flatten them out into a large number of parameters. And then right before the, then I densify that data. There's the dense layer by 64, and then do another dropout. And then the last layer is the dense layer. That's the actual output layer. And it's important you see that number 3 at the dense layer. That means that's for the 3 classes. So that number should always be the number of classes that you are trying to get out of your model. And the softmax activation is a probability array that comes out that tells you what's the probability that the pixel is in each of those, is in a certain class or not. Now here we're going to show how to actually run that code. This is going to create one task with 4 cores and then 48 gigs of memory. And then wrapping is just basically saying what is the command string that you want to submit to the cluster. And the code we just looked at was build model.py. And this is going to build a model and submit the batch to the batch. And then you can see if you take a, if you use your username and look in the queue, you can see where your job is. It's given it a job number, and the job number is waiting in the queue. It hasn't started executing yet. And you can keep looking and see when it has started. But at this point you can log off and log back in later to see whether your job is there, or has finished, or is in progress. And it will create a output file with your slurm dash and then the job number, so you can see what it output when your job ran. Now there's a bunch of detailed information that comes out first, but then you'll start to see the standard output from your actual code. So here are those statistics from the input data, the mins, maxes, means, and standard deviation. And then here we see how many, the clear, shadow, and cloud. That's how many samples were in our input data for each of the classes. But then as you remember, the shadow, I said, was the smallest class. So we resampled the data such that we only got 46,420 samples for each of the 3 classes. So that helps balance out our data so that one class isn't overrepresented. And then at the end, after the transposition, you see it outputs what the shapes are for the test data, for the fit data and the test data. Okay. Yeah, those are the number of balanced classes, and now the reshaped data. So we have 83,556 that are going to be used to fit the model, and then we're keeping out 55,704 to test it, to evaluate it. Now the next output is the summary of our model that we built with the different layers. So it's a sequential model, as I said, and then we see the convolution 2D layers and the number of parameters in each layer. Now that number of parameters, in this case, you can see that convolution layer was 32, and that 160 parameters is actually, I believe it's 32 times 3 plus 64. I believe that's how those the number of parameters is created. It's based on the number of the convolution as well as the number of classes. And then there's our dropout layer that has 0 parameters, of course, based on the way I described that as kind of forgetting some information to prevent overfitting. And then the next layer is the 48, the convolution 2D by 48. And that, I believe, is 40 times 160. That gets a number of parameters of 1,504. And then the flattening is we flatten all those multiple parameters down after the second dropout. And then that dense layer is actually the 196,608 times 64 gives us this huge 12,582,000 some parameters. That's what flattening out the dense layer does for us. So it in the end it produces a whole bunch of parameters, and then we do another dropout, and then our output comes out to the 3 classes. And so once we have run that, let's look at the output file, the bottom. Now it okay, it gives us the summary there, but now this shows each of the epochs. We ran it for 5 epochs where it learned over those 5 samples or iterations. As you can see, our accuracy in each is pretty high. It does increase, but it's about 95%. And then at the bottom there, if you see the confusion matrix, those are the 3 classes, the test data from the 3 classes showing which ones were classed accurately and which ones weren't. So here I'm just going to show this confusion matrix. These are the numbers that came from our output. Now here you can see that we have a 3 by 3 matrix, and the columns represent the predicted classes, and the rows represent the actual classes. So if you see here in the upper left corner, there were 18,228 clear pixels. There were 17,174 shadow pixels that were correct, and 14,626 cloud pixels that were correctly classified, as you can see in that diagonal. So this allows us to create what's called the user's accuracy, which is based on the number of actual classes actual number of pixels in each class that were correctly classified, and the producer's accuracy takes that percentage based on the columns, or the number of clear pixels in the clear column, shadow, and cloud. That's based on the prediction of those classes. Okay, now just to recap what we've covered here, we loaded the data and we scaled it and transposed it for TensorFlow. That was the initial part of the code that is available in the description of this video. Also, we built a model with the various types of layers. That's something that can change, and I won't go over how to tune models, but that'll be another video. We also fit the model to the data and created and compiled it, and then we assess the model with our test data. And then at the last part of the code is a step where we actually save the model to a binary file so that we can load it and use it again in other classifications. And we will cover that in future videos as well. So as you can see, my email is there, planetadvice@asu.edu. So if you want a kind of a consultation or have a bunch of questions about planet data, please feel free to get in touch with me. And I look forward to hearing from you. Thank you. Bye.